Okay. I have it. Yeah, got it. Okay. So, well, okay. Okay. So first, the motivation of our work is first try to understand the topological order and the codes, and or effectively long-range entanglement on fractal geometry beyond the usual scenario of manifold. Famous examples of fractals, including Sierpinski carpet embedding 2 dimension with fractal Hausdorff dimension DH equals 1.893, which captures how the system size of the fractal scales with linear size. And another example is the Mongoose sponge embedding 3 dimension. So a fundamental question we ask is, does a fractal quantum memory exist in nature, even just in 0 temperature? Here, by nature, we just means it's embeddable in 3 dimension. And another motivation from the perspective of fault-tolerant quantum computation is to reduce the space overhead, especially for implementing non-Clifford logical gates with topological stabilizer codes. There's a famous trade-off between dimensionality and universality, the so-called Bravy-Koenig bound, which states that logical gates implemented by a local constant depth circuit in D dimension has to lie in this level of Clifford hierarchy, which means that to get non-Clifford gates, you have to go to at least 3 dimension. So our idea here is essentially a code puncturing idea, which we want to dig holes in the code to form a fractal such that we can reduce the number of qubits while still preserving the code distance d, in this case, the linear system size, and also the ability to perform logical gates. So such that the scaling, which initially scaled with the integer dimension, now remarkably becomes the scaling with the fractal dimension. And then in particular, we want to reduce the space overhead of implementing logical CCZ gate, which initially need a d cube space overhead. So we start with the definition of topological order from the quantum information perspective. It is a geometric local physical system whose ground state subspace form a quantum code with a macroscopic distance d. And that means d scales polynomial with the system size L. And for any local operator which has support less than d sites, when it's sandwiched by the projector onto the code space, it's still proportional to the projector. This condition is essentially equivalent to the Knight-Laflamme condition. Now, from the geometric perspective, the code distance is also connected to the systole, and which is the shortest non-contributive cycle of metrical space. And this connection was first realized by Friedman-Mayer law. And this work is actually at the interface of quantum codes, topological order, and the systolical geometry in the context of fractal. So we start with showing the no-go result in 2D, and we start with the famous surface code, which is also equivalent as Z2 topological order. And that has 2 types of boundaries, the E boundary where the logical Z string can terminate, and the M boundary where the logical X operator can terminate. And we define the fractal iteratively by digging holes in smaller scales. And here the hole has the M type of boundary, which we'll call M hole. And this is exactly a Sierpinski carpet. And here L denotes the level of the iteration. And these holes can actually encode logical information. You might think they are useful, but they turned out to be curse in our case. So in all cases, you always have a pair of macroscopic logical operator, but when you dig holes, you introduce a smaller logical string, which can cross with the original macroscopic logical operator. And you stop the evolution when the hole size reach the size of the smallest, reach the size of the lattice constant. And in this case, you can see the macroscopic logical Z string always cross with a microscopic logical X string. So and they anti-commute. So the microscopic distance you have is order 1, and there is no topological order. And we also say there's a microscopic relative systole here. Relative just corresponds to the relative cycle connecting different boundaries. So in general, in the paper, we can prove a theorem that the Z and topological order cannot survive on a fractal embedded in a 2D Euclidean space. And The Z topological order here just is a generalization of the Z2 topological order, and you can consider the Zn version of the surface code where the qubits are replaced by n-level qubits. And also the theorem applies to a generic fractal arbitrary shape and also arbitrary boundary condition on these holes. More interesting case happens in 3 dimensions. We can consider Zn topological order in 3D, and we can write down exact model in the case of n equals 2 for the 3D Z2 toric code, where you put qubits on the edge, and you have a vertex type X stabilizer, and there's a placate Z stabilizer. We can also understand the theory from the topological quantum field theory perspective picture, and you have the E particle excitation, which violates the vertex stabilizer, and you have the M loop excitation, which violated the highlighted placate stabilizer. You can use a string-like Z error to create a pair of E particles, and you can also use a membrane-like X error, which we call X brane, to create an M string excitation. Also, this M string actually lives on the edge of the dual lattice, as we will see in the next slide. So another property in the TQFT is the gap boundaries in 3 dimensions, and similar to 2D case, you have 2 types of gap boundaries. You have the E boundary, which condenses the E particle, which means the Z string can terminate on this boundary. You also have the M loop or M string condensation on the M boundary, which means the X membrane operator can terminate there. Now we can look at the logical operators in the 3D surface code. So here, the top and bottom boundary are the E boundary, which also called the rough boundary, and the 4 sides are the M boundary, which also called smooth boundary. And the logical Z string live on the edge of the original lattice L. And we also introduced the dual lattice, shown by this thin green edge, where the qubits live on the placates of the dual lattice. And you can see the logical X operator is a membrane-like in the dual lattice. And in the QFT picture, it just corresponds to a single logical Z string cross a logical X membrane at a single point. So now we consider the fractal case. Similar to 2D, we can also define the fractal in 3D iteratively. And this particular geometry we call fractal cube geometry. FC 3.1 just represents the ratio between the system size and the size of the largest hole. And the cubic-like holes in this example is topologically equivalent to a 3-dimensional ball. And in general, we call this type of fractal a simple n-dimensional fractal, which is formed by punching holes which are homeomorphic to n-dimensional balls. So there are 2 types of holes similar to 2D case. And there's an E hole with E boundary, which can trap a logical X membrane and let the logical Z string to terminate. And a pair of them can encode a single logical qubit, which turns out to be a curse in our case. In contrast, you have an asymmetry that you have a M hole, which can not trap a logical Z string because you can shrink this loop continuously to a logical identity just by multiplying the Z stabilizer. So M hole does not encode logical qubit. That turns out to be a blessing. So first, we have a no-go theorem that if the fractal is formed by E holes, then you can see that a macroscopic logical X ring is always crossed by a microscopic logical Z string connecting the 2 smallest holes, and they don't commute, and you have the Z distance to be order 1, and you see you have a microscopic relative 1 system. However, if you have M holes, then you can have, on a simple fractal, you can have same topological order. And here we show the macroscopic logical operator on this model. So you can see that the logical Z string has to circumvent these M holes, while the logical X ring can terminate on the boundary of this M hole. And the smallest representative of logical X has a shape of a serpentine carpet. So we can show the essence of proof in the n equals 2 case. As we said before, the M hole cannot trap any non-trivial logical Z string. So that means the only class of non-contrapable Z strings must be associated with the macroscopic logical Z operator with this one, connecting different E boundaries. And the equivalent class of logical Z operator is described by the first relative Z2 homology group corresponding to the E boundary, which equals to Z2, means that you only have a single class of logical Z string. And the equivalent, similarly, the equivalent class of logical X operators describe the second relative Z2 homology group of the dual lattice corresponding to the M boundary, which is actually isomorphic to the first homology group due to the Poincare-Lefschetz duality, and it also equals to Z2. That just means the only class of non-countable X ring has to be associated with this macroscopic logical X operator. So there is no microscopic logical operator existing in this model. So we have a macroscopic distance and a relative C. So that's the end of the proof. So we now can consider code parameters of this class of models we call fractal surface codes. This particular example, FC31, has a fractal dimension 2.966, and the qubit number scales with this corresponding fractal dimension. And you have the code distance just equal to the Z distance, which is the linear system size L, which remains the same as the 3D surface code. We can also construct a family of codes, FCPQ, where P and Q represents the ratio between the system size and the hole size. And in this case, it's just the FC64. And you can derive formula for the fractal dimension. And in this case, it's 2.8, which is smaller than the previous example. And you can choose a family of these codes that Q equals P minus 2. And you can increase P and Q, which effectively enlarge the size of the hole. You can continuously crack down the fractal dimension into 2 plus epsilon dimension, which gives you a scaling of D to the 2 plus epsilon dimension, which has significant advantage compared to the 3D surface code. Now we could also generalize the result to an n dimension. We can define the so-called IN minus IZN toric code. Define it using a chain complex, where we put a qubit and the corresponding stabilizers on the cells of different dimensions. So in this class of model, the logical Z operator is always a I-dimensional brane, and the corresponding E excitation is 1 dimension lower. And similarly, the logical X operator is the M minus I-dimensional brane, which corresponds to M excitation is also 1 dimension lower. So in the case of I equals 1, so the theory has an E-particle excitation and a string-like logical operator, which is similar to the 3-dimensional surface code. While for I larger than 1, it doesn't have any particle excitation or string logical operator, and that's exactly the same case of self-correcting memories. So, so in the first case, when there's particle excitation, we can prove that topological order exists if the holes are M holes. That's just similar to the 3-dimensional case. More remarkably, so if you, in those self-correcting models, you can prove that the topological order exists independent of the type of boundaries. So the essence of this is the holes cannot trap either logical X or logical Z branes. For example, you have M hole here, which is n-dimensional ball with the boundary being n minus 1 dimensional sphere. And the Z membrane is a I-dimensional sphere. And here I is smaller than n minus 1. That means this Z brane cannot wrap around this n-dimensional ball, because it can always circumvent it by going into the extra dimension into the screen. And then you can shrink it into logical identity by just multiplying stabilizers. Similarly, the E hole cannot trap X membrane because M minus I is smaller than M minus 1. So that just means there is no microscopic logical rings, logical operators. So you have a macroscopic distance and a topological order exist. So that also suggests the existence of self-correcting memory in 3 plus epsilon dimension. So now we come to the logical gates. So we want to apply the logical CCZ gate. So that follows from the construction of the 3D surface code, where you put 3 copies of a 3D surface code where the logical Z strings are along different directions, and then you align them together to form a stack code, and you can perform a transversal CCZ, which will be the logical CCZ. So in our case, we consider 3 copies of fractal surface codes. So then this hole has a boundary which corresponds to 3 copies of M boundaries. We call M holes. So our first step is still apply a transversal CCZ. So that will preserve the external boundary like in the 3D surface code case, but it will map the M boundary into some exotic boundaries with non-Pauli stabilizers. So you can understand the essence by the fact that the boundary X stabilizer is conjugated by the transversal CCZ, and it's mapped to the product of X and the CZ operator on the other two copies, aligned with the X operator in copy A. So this kind of boundary has an exotic condensation property that it only allows the termination of the product of the X memory and the CZ memory on the other two copies. And so this first step implements a transversal logical map because it maps the original code space H to a different code space H tilde with different boundary. So now the second step is to apply a lattice surgery to map the code space back to the original one. So the logical information is encoded in the new code space with a new type of boundary. So we use another ancilla copy in the original code space with logical 0. And we apply a lattice surgery by doing d rounds of measurements to merge these two codes into a single code. Then you split it. Then you can measure out the original copy in the Z basis. Conditional by the measurement result, you can apply a conditional correction, a Z correction. Then you can see that the logical information is just transferred to the ancilla code block, which still is mapped to the original code space. So that completes the logical CCZ gate. So finally, we'll briefly talk about the decoder of the fractal codes. So for the Z arrow, we apply a minimum weight perfect matching decoder, and there exists a provable fault tolerance threshold for arbitrary code, fractal dimension. And we for this particular example of FC31 with fractal dimension 2.966, we perform a numerical study in an iterative manner that we dig holes in smaller scales while you increase the iteration level, L. So when the L goes to infinity, so you can approach the actual threshold of the fractal code. So in the L equals 0 case, you just get the 3D surface code, while this picture, and it has no holes in this picture, while this particular picture represents the L equals 2 case. So we can see a clear shift of the threshold when you increase the level, and there's a trend of the convergence to a larger threshold when L goes to a larger value. So one can conclude that the threshold increases when reducing the fractal dimension. So the essence of this is you can understand this because the logical failure rate is proportional to the number of non-contractible self-avoiding random walks like this. And they are blocked by the M holes because the E particle cannot condense on these holes. So that gets reduced, and that also decrease the logical failure rate. So use the same spirit, we could prove that thresholds approach those of the 2D surface code in the limit of 2 plus epsilon fractal dimension. So finally, we talk about how to correct the Z errors. So we use a cellular automaton decoder with local update rules, which is the so-called sweep decoder. That has self-correction and a single short error correction property. And then we adapt the original sweep rule in the 3D surface code. So here is the dual lattice, where you can see the X error is memory-like, and its boundary is the M string excitation, which also play the role of syndromes. And you choose a particular sweep direction. When a vertex is connected to two edges, which has an angle smaller than 90 degrees with the sweep direction, you can flip the corresponding placate. Then by repeating this, you can continuously shrink the X memory and clean the error. However, there's a challenge in our case because this M string could condense on this whole boundary. So you can see some sort of a metastable configuration like this, such that it's kind of a local minimum, and you cannot use the original sweep rule to kind of continually shrink it. So you have to modify the sweep rule, and you want to introduce some virtual syndrome on the boundary of the whole. And then use the modified sweep rule, you could continuously shrink this trapped error configuration. So we also can prove the threshold for arbitrary Hausdorff dimension in the case without measurement errors. When there is measurement error, we perform a numerical simulation for the same example, FC31, with this Hausdorff dimension. And interestingly, so we see that the threshold remains the same when you dig more holes and increase the iteration level. So and that doesn't change. And also we can increase the number of measurement rounds. And when this rounds approach to infinity, you can extract the so-called sustainable threshold. And in this case, it's 1.7% with measurement errors. And that stays almost the same as 3D surface code. Okay, so here is the summary of this talk. So we found that topological order on fractals can be understood with the TQFT plus defect picture along with the systolical geometry. And we proved no-go theorem in 2 dimensions. And we also proved the topological order exists in higher dimension if the boundaries do not allow condensation of particle-like excitations. And we find the non-cliff CCZ gate. And the time over here is still all the DROMs. And we found also discover a new gap boundary corresponding to non-Pauli stabilizers with exotic condensation properties. And we proved numerically simulate the threshold for both matching and sweep decoder. And the work in progress is really try to figure out a single shot non-cliff logical CCC gate, which could ultimately achieve order D to the 2 plus epsilon spacetime overhead. And that will have a significant practical advantage. So thanks for your attention.
Thank you, Guanyu. If there's a quick question to Guanyu, we can take one.
Hi. I wanted to ask about the no-go theorem for 2D. So you showed the distance was bad, is that right?
Yeah, it's order 1.
So does that guarantee that there's no topological order?
Yes, I mean, the definition is you need a macroscopic distance. So the physical meaning is that you need to protect topological degeneracy. So if you have a kind of a noise or any error of order 1, that can split.
Oh, so that's your definition?
Yeah,
okay.
That's kind of a common definition for topological order.
I think we should continue the session. Yeah, thanks, Guanyu.
Okay.